imagine holding a compass needle in a magnetic field. Turn the field very slowly, and the needle does not panic. It follows. The quantum adiabatic theorem says something similar about energy states. If a quantum system starts in one energy level, and the Hamiltonian changes slowly enough, the state tends to stay in the matching instantaneous energy level. Here the Hamiltonian, h of t, is the rule that defines the system's possible energies. Its eigenstates are the system's natural modes, like notes on a tiny quantum instrument. The warning label is the energy gap. If two levels come close together, the system can jump. A useful rule of thumb says, change slowly compared with gap squared. Bigger gaps make adiabatic following easier. Visually, think of a glowing dot riding one energy curve while the landscape bends underneath it. The dot is not frozen, it collects phase. But it avoids leaking into other curves when the motion is gentle. This idea powers more than a metaphor. It sits behind adiabatic quantum computing, where the answer is encoded in the ground state of a final Hamiltonian. Start with an easy ground state, slowly morph the problem, and hope the system tracks the lowest curve all the way to the solution. So the adiabatic theorem is quantum slow motion. Change the rules carefully, keep the energy gap open, and the state follows the moving path.